So I've got the USB attached here. This is the USB window, and I've got the calculator powered up and running. And I'll start it up. Startup window looks like that. Now, for some reason, I think it's to do with the level shifters or maybe the emulation, you can't plug the USB in and then start the calculator. The emulation doesn't work for some reason. You have to start the calculator, then plug the USB in. Although you can run with the calculator off, as it is at the moment. So what I'll do is start it up the proper way, like that. So we now have access to the USB of the calculator, and there are program steps available in the calculator. So this is the normal way it would be used anyway. The calculator would turn on. Then you'd attach the USB if you needed it. So if I do an H, I get the menu. So question mark does the same. That brings the help up. I can then do a D, and that displays the emulation memory. So this is the program memory of the calculator. Now the calculator stores this in a very strange sort of every 8 bytes reversed sort of scheme. Don't really know why, but it does, and this display unscrambles that, so that what we've got is 0 to FF in logical program order. And the reason for that is that I decode the keystrokes, and to get simple decoding of the keystrokes, I just have a setup where I look at the emulation around the program steps sort of in order from beginning to end. I'll type a short program in. Let's just put the short test program in PR1 or P1. So if we enter 1:2 : and then we go 3 = 1 times 2 : and the answer is in 3, so we display that with answer and then end. And then I do a D. You can see that we've got bytes, which is the program stored in program memory, so there's all the tokens that the calculator uses for those keystrokes. Down the bottom I've got the PR1, enter 1, 2, 3 = 1 times 2, answer 3, and end. Now I can run that and it'll work, but we're not really bothered about that at the moment. And you can't really see a lot on this display when you do that. So what else can we do? Well, we've got quite a lot of flash in the RP2040, and I can store in slots, program slots. There's 250 of them. I can store information in those slots, so I know that I've got a program in slot 10. So if I set up using Z to 0 a numeric parameter that I've got here, and then 1, 0, you can see that the parameter at the bottom there is 10. I can then display that slot. So uppercase D shows me that. Now this looks like the emulation memory, and it's a copy of it, but it's stored in the flash of the RP2040. And if I look at the emulation memory that the calculator is actually seeing, it's here. Now what I can do is use L to load that flash slot into emulation memory. So if I now look with D at the emulation memory the calculator is seeing, it's now seeing a completely different set of programs. So I can actually do on the calculator a PR1, and it's telling me I've got 144 steps left, which is less than I had just now. And I can step through this program and see the program that I've just loaded from Flash. I've got a similar command S, which stores the current emulation RAM in a Flash slot. Now with 250 slots, you could probably squeeze a few more out, but all I've done is divide the 2 megabytes of Flash that the RP2040's got into 2, so I've got about a megabyte. It's actually 1000K instead of 1024 to store programs in, and then the other megabyte is available for the actual firmware itself. that's quite a lot of slots. So I've allowed a scheme where you can label slots, and I can display those slots here. So this is showing me all the slots that have data in them, well, have a label in them and aren't blank. So if we have a look at 91, so if I do a Z to clear the parameter 91 and then a D, you can see that you've got a short program there which displays the word spice. Now the flash, when you write new firmware to the RP2040, it does not erase the flash other than the areas where the firmware is going to be. So as the firmware is in the lower 1 megabyte, these flash slots are retained across firmware updates, which is nice, and obviously still retained on power off. These programs have been here for, well, a couple of weeks now, maybe more. So you can load and save flash, you can label everything. I can do an A and display absolutely everything. So this is displaying every slot, and if there's something there, it'll put the label up and then display the keystrokes. If there isn't anything there, it'll just say blank, and that gives you a sort of, I suppose it's almost a backup. You can dump everything that's in the flash. I can also, with the W option and the address parameter that I've got, I can write a byte, an arbitrary byte, into any of the RAM locations of the emulation RAM, and that is the mechanism I use to determine what the codes were for the extra characters that are in the word spice in this program here. I actually I think that was 1, 2, 3, 4, 5, and then I went in and I manually changed the codes to spell out that word. So with the write command, you can actually experiment with undocumented features, and maybe there's some opcodes which do useful things, but it's quite a lot of work going through that, and someone who's got one of these calculators will have to do that. This isn't mine, this is here for repair, and it's going back, so I won't be able to do any more work on it once it's gone back. What else? I did put a toggle write protect in, but I found out pretty early on that the calculator actually rewrites its program RAM a lot, and it does it at times that you're not expecting. So I may be able to demonstrate here. We've got PR1 there, so if I go to write mode and do a PR2 and just put in some small program, there you go, that's a small program. Display that. We've now got a PR1 and a PR2, and it's PR1 first, then PR2, which is what you'd expect. But under certain circumstances, if I do a P1 colon and then do a display, PR2 is now at the beginning of memory, not PR1. It's swapped those programs around. How it does that, I don't know. Why it does it, I don't know either. I thought it was so it could do the step numbering in the display when you use the check key to go back and review the program. I thought it was something to do with that, where it could sort of not bother calculating it if the program was halfway through emulation memory, not do a subtract, and put the program that you're editing at the beginning of memory. But it doesn't do that. It's done the exact opposite here. So why it does that, I don't know. I do have a trace running in the emulation, so you can see there's the ampersand there. If I do that, this is a trace of accesses to the emulation RAM. Because I'm emulating the RAM, I can keep track of what's going on, so I can actually see the reads and writes and the data, and I've decoded the keystroke for all these accesses. Now these are byte accesses. I've formatted this in byte accesses. You can see on the left hand side I've got 1,000 entries in my trace buffer, and this is going from 0 to 1,000, but we don't have 1,000 byte accesses. We have less than that, because each bit that is read or written is part of a byte. So you get about 8 accesses. Well, you get 8 accesses for a byte. If you want to write a byte, you've got to write 8 bits. You want to read a byte, you've got to read 8 bits. And I've coalesced those down to make it easier to see what's going on. So from that you could probably keep an eye on and work out what is going on with the moving of the program steps around emulation memory, but I haven't done that. I haven't looked at it in massive detail. But there is a trace facility there, so you've got quite a lot of facilities to do with the emulation RAM. So yeah, write protect. I thought it would be an interesting thing to do. It turns out it's not. You just get an E on the display on the calculator, because the moment you deal with programs, it just doesn't work because it's moving them around a lot. What else we got? Well, the last one, the exclamation mark down there, is that is quite useful actually, because that is a command which will put the RP2040 into mass storage mode for firmware updates. And that means that you no longer have to open the case up and press a couple of buttons to actually upload firmware. You can just execute that command, the RP2040 goes into mass storage mode and then appears as a flash drive. You can then just copy the UF2 file over and you've updated the firmware, simple as that, and you don't have to open the case up. That is a nice time saver, and stops you fiddling around with the case and so on, which is causing wear to the plastic of the case and also the connectors. I've also got an information, uppercase I, which at the moment is just telling you whether write protect's on or off, and also how many reads and how many writes have taken place so far. So if I do that again, you'll see that nothing has happened because the calculator is just sitting there waiting for a keystroke. If I step a little bit through the program and do the same thing, you'll see that no writes, but there's been a few reads as I've read the program. So that's the USB interface. Some of these commands can be done on the keyboard of the calculator using a sort of mechanism to do with loading up program 15. So if I go to calculator and clear the memory, that is empty. If I then go back to write mode and put a program in, PR15 9 equals K, so now I can enter a constant. So if I display what we've got so far, 9 equals K. If I now do 11, so the first 2 digits of this constant are a command code. So 11 is load a flash slot into the emulation RAM. There's a status byte which is updated to show that the command has been executed. Some commands overwrite the emulation RAM and you lose your program 15, but some don't, and you can see that it's been completed or errored for some reason. 0 is the status. There you go, 110. Then you put the slot number in. If I put 090 like that, that is slot 90. And if I do a colon, you'll see that I've got the colon. The moment I do the end like that, you can see that the code picked up the fact that there was a command 11 in a PR15, dumped it and did the command. Now if I now do a display, you can see that the memory is totally changed, and that is the contents of slot 90. We can verify that. There you go, slot 90 is a program that displays ice instead of spice. That is the slot. You can see at the above the hex data, the slot 90. If I do D, your emulation RAM's actually got that in it as well. Program 15 has been wiped out, but obviously if you use program 15 to store the data in a slot, then program 15 gets stored with the program that you're trying to save, which doesn't happen with USB. USB interface, you can copy over the emulation RAM and you don't have any other steps needed to do it. From the keyboard you need to waste some steps to actually get that slot copied, or the RAM data copied into the slot. So there's a few commands. You can store the emulation data, so you can type a program in on the calculator, store it in a slot. You can also load a slot back. Obviously you can't label the slot, because trying to label it from a numeric keyboard is going to be terrible. You'd have to use the USB for that. I've also allowed writing a byte to an arbitrary location in memory and reading it as well, so you can read a byte and write a byte anywhere in the 256 bytes of the emulation memory. So without using USB, you could do some investigation into undocumented instructions, or put characters into constants and display them if you wanted to. Obviously it's easier on USB, but if you don't want to carry a computer around with you or something, or you want to write a program, then you can do it from the keyboard. So that's the USB interface.